All right, so in this video, we're going to talk through Chapter 7, the Time Value of Money, Part 1, Single Payment Value. So given a choice between receiving $1 today and receiving $1 a year from now, most people would prefer the dollar today. We recognize intuitively that $1 a year from now is not worth as much as $1 today. A lot of reasons for this. One would be inflation or rising prices erodes purchasing power. And at the time of this video, groceries is one major example where we've seen inflation be very high in the past couple of years. So what you can buy now for $1 won't be equivalent to what $1 will be able to purchase a year from now. And note that if there is no inflation, or if there's deflation or maybe even disinflation, where prices fall over time, we would have a different conclusion, perhaps. So maybe a question that would arise would be, well, what would make you indifferent between $1 today or $1 in the future? Well, the thing that would make you indifferent, we would need to consider cost, specifically the opportunity cost of money or interest and interest rates. So interest rates and time value money concepts link the present value of $1 and its future value. So if inflation ran at 3% annually, but someone promised to return $1 to you after a year with 3% interest, you would be made whole. You would be indifferent, in other words, to receiving either that present value dollar or its future value. So though inflation would erode the purchasing power of the dollar by 3%, the 3% interest you would earn offset the erosion of the dollar's purchasing power. Now, a couple of notes with this is that sometimes future cash flows are, they can be organized, predictable, and uniform sometimes. So when you receive a fixed regular payment into the future over a specified period, maybe like a rent payment, for example, or a lease payment, mortgage payment, those sort of things, that's called an annuity. And we'll discuss that later. Most of the time, however, your cash flows are not going to be orderly, and there's no discernible pattern to how they occur. So when in doubt, evaluate individual cash flows as separate lump sum cash flows in order to make sense of them. So a single lump sum present value is going to grow into a future lump sum value through something called compounding. Compounding at its core just means interest on interest, okay? So this is a sum of money that's invested over a span of time at an interest rate that will compound in value and grow to a larger amount. So for example, if you invest $1,000 for a year and the investment generates 5% interest per year, your investment would grow to be worth 1,000 multiplied by 1.05, or 5% of 1,000 is $50 plus the original 1,000 you invested, which would give you 1,050. Now, if you were to invest this for 5 years, let's say, and you let that interest compound, so you don't pull the money out, you just let the interest sit there and the interest compounds. So now you're getting interest on interest. You would get 1,000 multiplied by 1 plus that interest rate of 5%, or 1.05, 5 times. So it'd be 1,000 times 1.05, 1.05, 1.05, 1.05, 1.05. Or another way to write that would be 1,000 times 1.05 raised to the 5th power. Now note that if your investment didn't benefit from compound interest and you just earned something called simple interest on that, the $50, 50 times 5 is 250, and that's $1,250, okay? But with compound interest, we can see that instead of $1,250, we would get to $1,276.28, or that interest on interest we get, that compounding from year to year, yields us $26.28 more. So the formula for calculating the future value of a single present value payment is now on the screen for you. So FV stands for future value. This is equal to PV, the present value, multiplied by 1 plus the R interest rate raised to the N number of periods. Okay. With this one formula, we can solve all time value money problems. We can transpose this formula. We can solve for any other variables in the problem. As long as we have, some of the data, we can solve for any of these. Typically, a best practice for solving time value of money problems will be to create a table for each problem that identifies the known independent variables and the unknown dependent variable, the thing that you're solving for. And this table will help you sort the data such that you can use a financial calculator or Excel functions to solve the problem. So for example, we can rearrange the formula to solve for the present value of a single future value payment or lump sum by taking the original formula and dividing both sides by 1 plus the interest rate raised to the n power, and you get the formula you see there on the screen. So the present value PV is equal to the future value FV divided by 1 plus the interest rate R raised to the n power, the number of periods. Another thing we could do is instead we could solve for the discount rate or the interest rate, the rate of return. So opportunity cost considerations will drive our choice of the discount rate that are applicable to our time value money problem. We might know that a present value grows to a certain future value over a period of time, but we don't know what that interest rate is. In other words, we need to solve for the interest rate given that we know the present value, future value, and number of periods. So for example, if we were to invest $1,000 and after 5 years, the amount had grown to $1,250, we would have invested our funds at a rate of 4.56%, calculated using the formula that you see now on the screen, where R, the interest rate, is equal to the future value divided by the present value, raised to the 1 over n power, or the nth root, minus 1. We can also use this to determine growth rates. So for example, suppose the population of Mudville doubles from 2,000 to 4,000 in 20 years, and we want to know what is the average annual growth rate. Well, that would be 4,000 divided by 2,000 raised to the 1 over 20 power minus 1, yielding 3.53%. In this type of problem, it asks us to solve for n number of periods given the present value, future value, and a growth rate. So the math using this involves natural logarithms and is too complex to explain in this text. You can look that up on your own if you're interested. So we can use a financial calculator or Excel functions to do this work for us. So as an example, if you invest $1,000 now at 5% and want to earn $1,407 in the future, how many years would you have to invest this for? So in other words, the present value is 1,000, future value is 1,407, and the interest rate is 5%. You could guess and check to see what the number of years for that would be, or use the financial calculator or Excel to solve, and that would give you 7 years. So again, the best way to do this is to probably create a table that lays out the independent variables and isolate the variable that is dependent on the others, or in other words, the variable that you're trying to solve for. So the inputs tend to be PV, the present value, FV, the future value, N, the number of periods, and R, the interest rate. Make sure you input the independent variables first, leave the dependent variable for last because that's what you will solve for. Excel formulas work following the similar procedure. Identify the 3 independent variables and then solve for the dependent variable. So the Excel functions are as follows. To find the future value, FV, you need the interest rate, the number of periods, payment, which we won't discuss in this chapter, but we will later. So you'll need to skip that by either putting a 0 in or an additional comma besides the one you already put in. You'll need to put in the present value. And then the type is an optional argument. Typically, you will leave that alone. You don't have to put anything into that. However, if something is going to happen at the beginning of the period, you'll put the number 1 in there. Otherwise, just leave it alone. PV is found with the present value, and you need to put in the rate, number of periods, comma 0 or comma for payment for now, and then the future value. The number of periods can be found with the rate, skip the payment again, PV, FV, and then the interest rate is used using the rate function. Now with the interest rate function, since it's trying to solve something, Excel has this optional argument where you can try to guess it. If you leave that alone, which I recommend you do at this point, it automatically starts off at 10% and then guesses from there, adjust it. So time value money concepts will require you to answer the following types of questions. How much will I have in N years if I invest so much money today at a certain percentage and leave it untouched for N years? The independent variables in this case are PV, N, and R, and we're trying to find the future value. Suppose I need so much money for a down payment for a house in N years. How much money must I invest today at whatever percentage annually? In this case, the independent variables are the future value, N and R, and the dependent variable is present value. If I invest dollars today at percentage and want to grow it to dollars, how long must I wait to achieve this goal? The independent variables are PV, FV, and R, with the dependent variable being N. And then lastly, at what rate of return must I invest dollars today if I want to have dollars in N years' time? You would need PV, FV, and N. That's your independent variables, and you're trying to find R. Note with the last two questions, if you're asked the following question, which I've seen happen quite a lot in interviews, how long or at what interest rate would it take me to double my money? What you can do is take the number 72 and divide it by either the number of periods that you're given, number of years, or by the interest rate that you're given, and you can respond to the answer very quickly with a back of the envelope calculation with not too much rounding error. So for instance, suppose I want to know how long it would take me to double my investment at 8% interest. The answer would be 72 divided by 8, which is 9. And then maybe again, suppose they ask you the question, okay, I have 10 years to double my investment. At what interest rate would I need? You would say 72 divided by 10 or move the decimal place over 1, and that could give you 7.2%. So note that inflation is defined as a period of rising prices. With inflation, a dollar in the future will not have the same purchasing power as a dollar today, as inflation will erode the purchasing power. If one were able to invest money at the same rate as inflation, one would not lose purchasing power. So deflation, or a period of declining prices, would have the opposite effect. Now, investors want to know the real interest rate, not just the nominal interest rate or what's stated or told to you. They want to know how their investments are going to be affected, regardless of inflation. So there's an equation called the Fisher equation, where we take 1 plus the nominal interest rate I, and we set it equal to 1 plus the capital R, the real interest rate, multiplied by 1 plus H, which is the expected inflation rate, and we can solve for whatever variable you're looking for there. Also note that investors want to generate a rate of return that's commensurate with the level of risk that they take on. The risk-return relationship reflects the fact that risk and return go hand in hand. Investors are normally risk-averse. They don't like risk. Okay, they want to try to avoid it. But rather, they will, accept the risk only if they receive commensurate compensation for the level of risk that they take on. So investors also approach the topic of investing through the lens of opportunity cost. So quoting here, if I am to invest in this project, it must earn at least the rate of return that is its next best alternative. In other words, the rate of return that I forego by making this investment. The risk of default, or the borrower not being able to pay back the money lent to them, is a risk that investors are most eager to be compensated for. A couple of more notes here. The more frequently interest is compounded, the larger the value of the future lump sum. So for example, if I invest $1,000 at 6% per year compounded once a year, that would be 1,000 times 1.06 to give me 1,060. However, let's suppose that it's compounded semi-annually or twice a year. What you would do in this case is you would divide 6% by 2 to give 3%, and then I would multiply it twice. So it would be 1.03 squared instead of once, as we saw earlier. So 1,000 times 1.03 squared gives me $1,060.90. So because it's compounded twice instead of once, I have 90 cents more of compound interest. And then lastly, if I invest $1,000 at 6% and it's compounded quarterly or 4 times a year, 6% divided by 4 is 1.5%. And then I'm going to raise that, instead of the first power annually, I will raise it to the fourth power because it's compounded quarterly. So 1,000 times 1.015 to the fourth power would yield $1,061.36, which gives me 46 cents more compound interest than semi-annual or compounding twice a year. and then it gives me $1.36 more, respectively, than compounding once a year. So the more frequently compounding takes place, the greater the future value. So now to conclude, the future value equation must be adjusted for the number of compounding periods when compounding more frequently. Recall that's the future value equals the present value times 1 plus the interest rate R raised to the n power. So here are the adjustments. When the number of compounding periods is n is 1 per year, the R that is input into the equation is the annual interest rate. When the number of compounding periods is 2 per year, or semi-annual, then n must be multiplied by 2, and the annual interest rate R must be divided by 2 to get a semi-annual interest rate. When the number of compounding periods is 4 per year quarterly, then n must be multiplied by 4, and the annual interest rate R must be divided by 4 to get a quarterly interest rate. So this concludes our introductory lecture regarding time value money, and specifically how to solve problems with lump sums. The next 2 lectures delve further into more complicated and complex time value money problems. Thanks for watching this one, and I hope to see you in the next one.